So today we are going to understand what are the eight axioms that must be satisfied for a set of vectors with scalars from a field to form a vector space. Previously, we tried to understand what does a field means. So a field is something that has all the scalars with inverses except zero. So we also saw integers and why they are not a field because there does not exist inverse. For example, for -2, we are not able to find any inverse. Basically, for inverse, it means that if we multiply the inverse has to be present in the set. Okay. So for -2, is there 1 by 2 or -1 by 2 anywhere? No, it is not present in integer because integer is always a whole number. So therefore, we concluded that integer is not a field. So for today, let us say you have a set of vectors. Maybe you are going to solve something and you came across collections of many vectors. Now, if you want to solve it in a particular way that we will see in future, so we have to understand first of all if this set of vectors that I have collected forms a vector space, and to form a vector space, it must have followed the field and also the eight axioms. Okay. So the first axiom is the addition axiom. Exactly, there are four of them, and then four are for multiplication, and one is identity. So maybe in some books you must have seen 10 axioms, but basically we compress it to eight axioms because two of them are redundant. So the first one is, as I said, first one is commutativity of addition. Commutativity of addition. What does it say? It says u plus v equals to v plus u for all for all u and v and v in v. So this symbol means for all or all. Actually, this symbol that I just wrote, first of all, for us, math is hard because I am from a non-mathematical background, or for any one of you. The first thing is we don't understand how to speak the language of symbols. So here I will try to help you understand them if you go to my video. Basically, this video is just for my revision, so you can create your own as well. So this is kind of called as universal universal quantifier, which represents for all or for every and used to say that it stands for all or every element in a given set. Okay. So next we will proceed further. So you can say u plus v equals to v plus u. Either way you add them, The result is same for every, okay, for every U and V, which are elements of the set V. Okay, this symbol represents element, E symbols. This symbol, let me tell you. Oh, I'm using it also. Yeah, this symbol. Hmm. So this is element for every element. Okay. Now the second axiom, which is related to addition, is associative associativity. Associativity of addition. So we can say if we have multiple elements, we are trying to add u plus v close brackets plus w equals u plus open bracket v plus w for every u v w which belongs to set v. As we said earlier, every element u v w which belongs to set. Now the third is existence of additive identity. Okay, so existence of additive identity sense of identity. So there exists a zero vector. There exists a zero vector in V such that such that V plus zero equals V for all V in set 2. So you can say every, or we can say mm, there exists, what am I doing? There exists zero element in set V such that V plus 0 equals to V for every V element present in the set V. Now the fourth one is existence of additive inverse. Existence of additive inverse. So for every element V present in set V, there exists a negative V element inside the set V such that when we add them V plus negative V equals to 0. Okay, so these were the four axioms related to addition. Now we will move to Scalar multiplication axioms. Scalar multiplication axioms. Okay, so first one is distributivity. Distributivity of scalar over vector addition. So A times U plus V equals to AU plus AV for every A element present in a set V. Uh, okay, for every element, for every scalar, for all scalars, A element present in F and U, comma V in V. Okay, so you must be now thinking, isn't F and V two different sets? Let us understand this. Just as you can conclude, what is F? F is a set of what scalars? We did not see this in addition when we were checking the additions axiom, because there we are only checking if the set of vectors in V, set of vectors present in the set V, any element, each element represents a vector. So if any one of them are present in, so there we were doing the addition, so we just needed that vector set. Here we need a scalar as well, and so therefore the F is set of scalars, and these scalars can only come from fields, not from non-fields. Okay, so this must be clear. It is clear to me. So next, we have what is called as distributivity of scalar addition over vectors. Distributivity of scalars of scalar addition, scalar addition over vector. So A plus B into V equals to A plus B V, where for F3, for F3, A, B, which are element of scalars, say F, and V, which is an vector element from set of vectors V. Okay, so next one of the axiom is Associativity or scalar multiplication. Multiplication. So we can say A times BV equals to ABV, just like the associativity in addition, but here we have for every AB, which are elements of set of scalars called F, which comes from a scalar field, which can be rational numbers, complex numbers, real numbers, whole numbers, etc., but not integer. Okay, and element vector V from a set of vectors set vector set V. The each one, the final word is called IDT scalars. T scalars, which means 1 times V equals V for every V, which are vector elements in set V, which is a set of vectors. Okay, next we will try to understand if a set or if a set is a vector space or not. Let me rephrase the question more clearly. Okay, now let us assume a situation. So as to rephrase my question correctly, uh, we have, for example, you maybe I went and collected a set of wavelengths. Okay, maybe not wavelengths, anything else, and we would just want to check that if the collection of these vectors that I just collected is a vector space or not. So first of all, what are basics say? For a collection of vectors to be in vector space, it needs to follow two operations, multiplication, scalar multiplication, and addition with 8 axioms that needs to be satisfied. So we will need to check if we satisfy all these axioms, only then we can say that it is a vector space. Okay, to understand it in more detail or maybe deeply, we will try to prove this in R3. Okay, so the first question arises is what is R3? So you can think of R3 as a 3D vector. Maybe you come across a situation where the set of vectors that you collected is kind of 3D vectors. Okay, so you collected 3D vectors that has values x, y, z, and there are many of these, maybe millions or maybe few hundreds. Okay, so let us try to prove a vector space axioms for R3 one by one, one by one. So to do this, or whenever we do something, we have to first define what do we need to define here is R3. So we define it as R3 equals to X, Y, Z, where X, Y, Z belongs to element. X, Y, Z are the element belonging to a set R, and set R can be S. For this example, we can say real number. Okay. So we can say x1, y1, z1 plus x2, y2, z2 equals to x1 plus x2, comma, y1 plus y2, comma, z1 plus z2. A comma A times x y z equals to ax comma ay comma az. Okay, for scalar A that belongs to set R is a real number set. So for first, let us start with first axiom, that is commutativity of addition. Of addition u plus v equals to v plus u, as we studied earlier, for all elements q, comma v belonging to, so means uv are elements that belong to set R q. Q is 3D vector. Okay, sets. Here we have u equals to x1, y1, z1, and v equals to x2, y2, and z2. Then u plus v equals to x1 plus x2 plus y1 plus y2 plus z1 plus z2, and v plus u equals to x2 plus x1 comma y y1 plus y2, sorry, y2 plus y1 comma z2 plus z. Similarly, associativity of addition would also be same. So what was associativity of addition? Associativity of addition. What was it? It said u plus v plus w equals to v plus v plus w for all u, v, w elements belonging to vector set of 3D, sorry, vector 3D vector spaces. And So basically, if you take here x comma y comma z plus x1 y1 z1 plus x2 y2 plus z2 plus x3 y3 plus c3, it would satisfy this associativity of addition. Similarly, it should satisfy all the axioms if you want to consider it as a vector space. So if you want, you can think of a real life example where this may work, which in this case can be, as I have seen and searched on the internet, the most simple thing that I was able to find was loops 3D, where what the scientists did was we measured three components of electric field produced by cosmic ray air showers at antennas. There were many antennas, so they were a kind of east, west, comma, north, south, and vertical polarization. Okay, so they received the signal, and signal received from this would be one component, from this would be second component, and from vertical would be third component. So this all three is R3. And together with many of these vectors, 3D vectors, we will have a vector space if it follows two operations plus a axioms. Now we will move to what are subspaces. Okay. Okay, so let us try to draw a simple mental model or maybe graph. Let us say you have got a collected set of vectors. For example, maybe 3D set, can be 2D. Okay. For example, x, comma, y, comma, z. Once we have these vectors, let us say this is R3. We try to check it over a field to confirm if R3 is a vector space in field F, where F can be complex number, real numbers, rational numbers. So this is clear to us now that what is a vector space, followed by 8 axioms. Okay. Now what about subspaces? As we can deduce from the term subspaces means we take some part of it. It can be only Y, it can be only Z, or it can be YZ, or it can be X, Y, Z. Okay. So if you take Y, this will be a one-dimensional. If you take two components from it, it would be 2D, can be 3D. So subspaces from a vector subspace, sorry, subspaces from a vector space can be equal to it or less than it. Therefore, it should also follow the same 8 axioms plus what addition, scalar multiplication, which is exactly what 8 axioms tells us. However, there is also important thing to notice. Not every part can be called a subspace because we always need zero. Zero must always be included. Even if we take 1D, if we take elements y, z, x, so on, zero must be included in it. If we take y, z, it has to have zero. Okay, zero is zero, zero. Why? Because without origin, this would be not useful because using vector space, what we are trying to usually model linear, linear model, which is predictive.